Hi, welcome back. So, this is lecture 37 in this course on Bayesian modeling. So, the topic of this lecture is HMC implementation. So, we will learn how to implement a Hamiltonian Monte Carlo sampler in R or any other programming language. Okay. So, we will say step by step how to break down each step in Hamiltonian dynamics and then implement its sampler in R. Okay. So, just to recap what we discussed so far yesterday. So, the idea behind HMC sampling is this, that we want to use the geometry of the posterior distribution to inform our proposal generation. So, we do not want to randomly walk on a flat surface to explore the posterior distribution, but we want to use the geometry of the likelihood into prior. So, basically the exploration of parameter space is informed by geometry of the posterior distribution. So, I discussed some of these things. So, the key difference is in random walk versus a slide along this surface, right. So, in random walk algorithms, for example, in simple MCMC metropolis hashing algorithms, we randomly jump from the current location to a new location in the parameter space. So, the only information we are using is the current state of the chain. So, basically the proposals that you have already sampled, parameter values that you have already sampled from the posterior, right. You are not using any other information. In this case, we are using information of the current state. So, parameter values that you already sampled, as well as we are also using the geometry of likelihood into prior function to inform our next step. So, we are not randomly jumping from current state to next state, but we are just taking a slide along that curve, so that we most of the times we would land in higher posterior density region. So, that is the idea, and this is how we implement it. So, we take negative log of likelihood into prior. So, this is how the negative log of likelihood into prior would look like, and we can think that let us say there is some particle somewhere on this surface, and think of this surface as a frictionless surface, and we push that particle in either direction with some momentum. So, either you can push it upwards or downwards with some momentum. So, this particle will slide downwards, let us say will go up here and will come down. So, all those things will happen, but what we are interested in is in recording after some time t has elapsed, what would be the new position and new momentum of the particle. Okay. And given that new position and new momentum, we can calculate total energy of the particle in this new state. So, total energy would be a summation of kinetic energy and the potential energy, and we will compare whether the total energy of the particle in this new state is lower than the total energy of particle in its previous state. If it is lower in the new state, then we will accept that new state, right. So, we will accept a state with lower energy. Okay. So, particle would want to remain in lower energy state. So, that is the idea. So, we say that there is a frictionless particle of mass m sliding over a frictionless surface, and we define this dynamics using total energy, which is a summation of potential energy and kinetic energy. Now, potential energy will be given by how high is this, basically will be defined in terms of mgh, right. So, remember the formula potential energy. So, it would be a function of how high is the particle on this surface in a particular position, right. So, if you think of x axis as parameter space, so these are parameter values, right. So, y axis denotes the negative log of likelihood and prior. So, corresponding to any position, you can calculate negative log of likelihood into prior, and that is the height of the particle, and that is what will give you the potential energy of the particle. Okay. So, you can always calculate this potential energy of the particle for any position, right. All right. So, then we saw these Hamiltonian equations which we require to solve this problem, that where would particle be, what would be new position of the particle after time t. So, we need to calculate that, right. It is unlike random walk algorithms, we are not generating new state from any density or from any well defined proposal distribution. We need to calculate what would be new state after time t. Okay. So, this is not a straightforward, this is going to take a lot of algorithmic steps in order to do that, right. So, we do this using these Hamiltonian equations. What these equations do, that they give us the rate of change in position and the rate of change in momentum as a function of basically as a gradient of energy. So, for example, rate of change in position is delta H by delta rho. So, basically change in total energy with respect to momentum. Now, because potential energy does not depend on momentum, so we can simply write change in kinetic energy with respect to momentum. And here change in momentum, rate of change in momentum is given by negative of change in total energy with respect to position. So, which will again become, because kinetic energy does not depend on position, it only depends on momentum. So, we can write change in potential energy with respect to position, right. So, this is how we can write these equations. Okay. Now, given some initial position and initial momentum, let us say theta I and rho I, our goal is to calculate what would be the new or proposed position and momentum after time t. Okay. So, that is our goal. So, we will stop the particle after time t and we will observe its new position and new momentum. Okay. So, this is the formula of potential energy, negative log of likelihood into prior, right. So, these are the steps in the algorithm. So, in each iteration the particle will be pushed from its current position. So, basically current state in random direction with some momentum. So, in every iteration we will push the particle in either direction with some momentum rho I, and after time t has elapsed, the particle of course will acquire new position theta j and new momentum rho j. So, that is what we want to observe. So, we will calculate what is this new position theta j and what is this new momentum rho j, and then we will calculate total energy of the particle in this new state and the previous current state, right. And if the energy is lower in this new state, we will accept that new state, right. But in order to calculate new position and new momentum, we will need this leapfrog method to discretize Hamiltonian equations. So, what we do is this: we do half step update for momentum. So, we will do this for L number of times, because we discretized our time capital T as L into epsilon. So, like this, right. So, we discretize this time t into L number of small time steps, where epsilon is indicating a very small time step, right. L is the number of leapfrog steps, right. So, for L number of leapfrog steps, we will do these things L number of times. So, each time we will first update momentum. So, momentum will be rho minus, so basically whatever initial momentum was there, rho minus epsilon by 2, and then change in momentum with respect to time, right. So, which is basically change in potential energy with respect to position, right. And then full step update for position, and then again half step update for momentum. We discussed this briefly in the previous lecture, right. And then once you have achieved new position and new momentum, once you have calculated that, you can calculate total energy of the particle in these two states, right. And then we can calculate that the system would want to remain in a lower energy state. So, we can calculate probability of transitioning to this new state j, right. So, this is how we can calculate probability of transitioning from I to j would be given by e to the power h I minus h j divided by k t, right. So, that is the idea. So, the particle would acquire new state with this probability, right. So, let us see step by step procedure, and let us take some example, okay, and using that example we will see step by step procedure of implementing an HMC sampler. So, let us say this is the example. You are given 500 data points that are assumed to come from a normal distribution with mean mu and variance sigma square, okay. So, you have 500 data points, let us say from an experiment, and you assume that these data points come from a normal distribution. So, that is your likelihood assumption, okay. Then you need prior assumptions on mu and sigma. So, let us say prior assumption on mu is that it comes from a normal distribution with mean m, standard deviation s. Sigma comes from a normal distribution with mean a and standard deviation b, okay. So, this is fine. So, so far these are our assumptions about prior assumptions and the likelihood assumption, and let us say this is your data. Now, step 1 will be to define gradient function. Okay. So, this is an important step, because basically once you have defined gradient function, then then your work would become easier. So, in this part, because you need to do some analytical calculations, right. What do I mean by defining gradient functions? You need to define rate of change in position with respect to time, rate of change in momentum with respect to time. So, basically you need to do differentiation of potential energy and kinetic energy respectively, right. So, this gives you the potential energy, negative log of likelihood into prior. Okay. Now, you can plug in what is the likelihood function. So, likelihood is a normal likelihood. So, I am just directly plugging in likelihood function here. This gives me prior density for mu, this gives me prior density for sigma. Okay. So, basically this function gives me negative log of likelihood into prior, right. It is a complicated function, but what all I have just done here is that I have taken log of likelihood into priors, okay, and I have expanded them in the PDF, right. So, of course, here you have multiple data points. So, y is a vector of n data points. So, here whatever y I you are seeing, it is basically each ith data point, right. So, likelihood will be basically a joint likelihood. So, basically I am taking summation of negative log of these likelihoods of each independent data point, right. So, this is what the final form becomes of this function. I simplify it a bit and expand it on some parts. So, this is the final form of my potential energy. So, which is negative log of likelihood into prior. And then I differentiate this potential energy function with respect to position. So, in this what does position mean? Basically your parameter space, your parameter value. So, position of the particle in your parameter space, that means the parameter value, right. So, we have two parameters here, mu and sigma. So, I differentiate this potential energy with respect to mu and with respect to sigma. Okay. This is exactly what will give me change in momentum with respect to time, right. So, remember the formula for Hamiltonian equation for change in momentum with respect to time here. So, change in momentum with respect to time is given by negative log of change in total energy with respect to position, which will be negative of change in potential energy with respect to position, right. So, this will give me rate of change in momentum. So, this particular gradient. So, this will give me rate of change in momentum. Okay. About the second gradient, so what will be change in position with respect to time? That would be easier to calculate because that is just differentiation of kinetic energy function. Okay. And kinetic energy is what? Rho square by m, rho square by 2m. So, if you just differentiate it, what you will get is I think just rho. Okay. So, that would be the differentiation of that function, right. So, in the second case, the change in position will be equal to just momentum, right. So, that would be easy thing to do, right. This one was difficult because you needed to differentiate the whole likelihood into prior, negative log of likelihood into prior function. Okay. Now, what I am doing here, I am basically encoding these functions in R. So, this is the gradient function which gives you gradient for mu and gradient for sigma. So, differentiation of potential energy with respect to mu and with respect to sigma, and I return these gradients, right. So, the function takes value of mu, sigma, data, number of data points, right, and then these are the priors, right. This m and s, this makes the prior on mu, this makes the prior on sigma, right. So, I give all these arguments and this function will calculate gradient for mu and sigma, of course under these likelihood and prior assumptions. If your likelihood and prior assumptions are different, then of course you will have a different gradient, right. That is why always first step is to, depending on what your likelihood and prior is, you will calculate these gradients, right. Also total energy function and potential energy function. So, for example, here I am calculating potential energy function. So, I am passing same arguments mu, sigma, yn, ms, ab, and this calculates the potential energy function for me. Okay. So, potential energy function is basically this, right. So, this thing, the simplified form we have here. Okay. So, this is what I have done here. Okay. So, once I have these two functions, then I am good to go because now I do not need to do any further analytical derivations. I can just use these functions for further sampling, right? So this is how the HMC sampler looks like. So first time is just storing the data and these things. These are model parameters, basically priors. This was prior on mu, this is prior on sigma, right? So once I've defined priors and everything, then I need to define step size parameter here as well, right? Remember, we discretize time, capital T, into L number of into L leapfrog steps. So we discretize capital T equals to L into epsilon. This is that epsilon. Okay, so time step. So how much, how big or how small time step you are taking, right? So we will multiply this with L to get time, right? And you also need to define number of leapfrog steps. So here I have defined, for example, 20 leapfrog steps, right? You can define 12, 15, 20. I think all this works fine. Okay. And this is the number of this is the step size, right? If you multiply this with this, you get capital T, right? Now I decided that I would want 8,000 samples in my Markov chain. So I initiate an empty Markov chain for mu and sigma, for both mu and sigma, okay? And then initialize this Markov chain for mu and sigma both. And then I start defining, I basically, I now define how I would evolve this Markov chain using Hamiltonian dynamics, right? So all other things would remain same. Only thing you need to figure out that how do you generate new proposal. So that's the step that will be different in case of HMC, right? So this is the current position of the particle Q. So basically this is the current state of both mu chain and sigma chain, right? Q is the current state of mu chain and sigma chain. P is basically, you can also call it something else, maybe R or something. So this is the random momentum we are generating from a normal distribution. So we are randomly generating momentum from a normal distribution. Basically this will push the particle in either direction. Okay, so because it can have negative as well as positive value. And then I store current Q and current P like this, and then I can calculate potential energy and total energy of the particle in the current state, right? So this is potential energy in the current state, this is kinetic energy in the current state. What I have to do now is to calculate what will be the new position after time t. So in order to do that, I discretize time into L leapfrog steps and I iterate through each leapfrog step. So I go for L in 1 to L, and each time I do this, that I update P, right? So I update momentum. So half step update in momentum. So step by 2 into gradient, right? Then full step update in position, Q, Q plus step into P. So full step update into P, basically because the gradient will be just rho, the momentum, right? And then half step update in momentum. So P will be then P minus step by 2 into gradient, right? So this is how, so the finally after L steps, the final position of P and Q will be my proposed P and proposed Q. Okay, so like this. So now I can calculate potential energy and kinetic energy in this new position, right? So this is potential energy of the proposed state and this is kinetic energy of the proposed state. And now I can calculate acceptance probability. So all I need to do, I'm just taking exponent of current V plus current T minus proposed V minus proposed T, okay? And then I take minimum of this, right? And then I basically make a criteria based on this acceptance probability, right? So I can generate, for example, from a Bernoulli distribution. So that's the idea. So if acceptance probability comes out to be greater than 1, basically this thing comes out to be greater than 1, then I will always accept, and this will come out to be greater than 1 only when the total energy in this proposed state is lower than total energy in the in the current state, right? In that case, this would be greater than 1. So, in that case, we will accept all those proposals, right? And the rest of the things are same. So, that is the basic sampler for Hamiltonian Monte Carlo. So, let us implement this in R. So, first we need to define the gradient function and the potential energy function, and then we can go on implementing this sampler, right? So, I will just copy paste the gradient function for this particular example of normal distribution. So, the gradient function is given by this, and the potential energy function is given by this. Okay. Now, let us implement HMC sampler. So, first let us have data. So, let us say this is your observed data y, and let us say you have 500 data points. So, from a normal distribution with mean 800, standard deviation 50 or so, or it's 80. This is your data. N is length of so basically number of observations, and then of course these are your likelihood and prior assumptions. Then yi, each data point comes from normal mu sigma, where mu comes from normal ms and sigma comes from normal AB. So now you need to define what is MSAB to define the priors, right? So let's say we can use the same priors as used here. So let's say M is 1000, S is 100, A is 10, B is 2, oh not 10, 2. So maybe A is 50, maybe 60, 20, something like this. Now let us implement HMC sampler. So let me define a function HMC in the same way as we defined for MCMC. Of course, we need number of samples. So let me just start with 5000. You need a step size. Okay. Let's say time step, at least a step is let's say initially 0.02. You can of course change it later. You just need to give in details in this. Then reject is equals to 0. So you also want to count rejection rate, right? So this is all fine. Now how do I begin? I will first create empty chains, right? So I will create first empty mu chain of how many samples? N samples. Then sigma chain containing how many samples? N samples, right? Then I will need to initialize these Markov chains. How do I initialize them? So let's say mu chain. To initialize, I can write I equals to 1, and mu chain I comes from, let's say, R norm MS, it's prior, and sigma chain I R norm comes from its prior. Okay, so I've initialized the chain. Now I need to evolve these Markov chains, right? So let me just get this code here. Okay, or if you want, you can write it with me. So let us think of what is the current state or the current position. Okay, so let's say to indicate current position, you use this Q. Okay, so Q indicates the current position. So both chains, right? So value of mu and corresponding value of sigma. So it would be pair of value of mu and sigma that will state the current position of the chain, right? So you can write it like this: mu chain I and sigma chain I. So this is the current position. For current momentum, you need to randomly draw samples from some distribution. So let's say I randomly draw samples from an R norm distribution, and I need to draw two samples, one for mu and one for sigma. Okay, and I draw them, let's say, from 0, 1. Okay, so this will give me momentum. Okay, so I can call them current position is Q, current momentum is this P. Okay, now once I've recorded current position and current momentum, now I can calculate potential energy in the current position. So current V. Current V will be, I will just call this function V and will pass on all these things, mu, sigma, yn, ms, ab, right? So in this function, I will pass on mu. So mu sigma would be given by just, let's say, q1, q2. q1 is mu, q2 is sigma, right? Mu sigma yn, ms, ab. So yn, m, s, a, b. Okay, so this is current V, and current T, kinetic energy, will be given by P square rho square by 2. Okay, so this will be kinetic energy, right? So now you have current position, current momentum. Now you need to push the particle in either direction with this particular momentum P, and you will record the particle after time capital T, right? And we discretize this capital T into L number of leapfrog steps, right? And the step size is defined by this particle step, right? So I will run this loop through each leapfrog step. So basically I will iterate through each leapfrog step, and then I do half step update for momentum, full step update for position. So here I'm doing half step update for momentum, full step update for position. So after this point, I will get basically new position and new momentum, and then I can calculate basically proposed the total energy and other things in that new position and new momentum. Okay, so this becomes the proposed Q. So after L iterations, whatever value of Q would be proposed Q, proposed P. So I'm calculating potential energy in this new state, kinetic energy in this new state, and then acceptance probability would be total energy in current state minus total energy into proposed state and exponent of it, right? So that this would give me some measure of probability of transitioning from the current state to proposed state, right? Now I can use acceptance probability in the same way as I've used earlier. So I can generate acceptance criteria. How? So acceptance criteria can be generated by R by norm 1, size equals to 1, probability equals to acceptance probability. So if accept is equals to 1, so if you need to accept, then you accept this new particle. How do I accept it? I will update the position of the chain and I will store it like this. So mu chain I becomes proposed Q1 and sigma chain I becomes proposed Q2, right? Else I won't update this, I will only update number of rejections. So this is the sampler. All right. So this is a function that will implement an HMC sampler. Okay, except not found somewhere. So that's acceptance probability 0.8. Right, so why this step is not working? Okay, I need to replace these signs. All right, so let's see. Okay, this should work now. So now let us define number of samples equal to 5,000 or so, or let us just keep it at 5,000. Let us just run this sampler. Okay, so chain 1. Oh, I haven't written the return function, which I should write here. Return samples equals to data frame mu chain, sigma chain. So I'm going to return the posterior samples as a data frame. That would be easier to use, so that okay, L is not defined. Okay, I think it is done. So let us see. So let us see if we are able to do sampling for samples. So let us see samples of mu. Oh, so there's some problem in this. Okay. Uh, let's see sample of sigma. Okay, so apparently the function is working, but there are, I think, some minor issues in this code. So that's why the sampling is not properly done. So we will take a look at this in the next lecture. Okay. So the purpose of this lecture was to show you that how we can implement an HMC sampler in practice, right? So in practice it requires much more work. So basically you need to define your gradient functions, your energy functions, and then use them to calculate new position of the particle after time t, and then you can do all the same things to determine acceptance rejection criteria, right? So as you realize that this is a really good sampler, by the way, that we will see in next lecture, but it is difficult to implement as you go towards complex likelihood, and primarily because it becomes you will have to calculate these gradients and potential energy for every likelihood into prior and then implement it, right? So we will be using well defined packages in R, for example BRMS package, to do sampling for us using Hamiltonian Monte Carlo, right? And that's what I will also show you in the next lecture, that how do we get posterior samples using HMC using this BRMS package. Okay, so we'll discuss that in the next lecture. All right, so thank you very much. I'll stop here. I'll see you in the next lecture. Thank you.